Welcome back to the deep dive. We've got quite a stack of sources here, all focused on the stuff the world's made of, the properties of matter, solids specifically.
That's right. We're looking past the surface today.
Yeah, trying to understand what literally holds things together, the hidden physics behind solids and structures.
And the goal is really to get a quick handle on how that internal structure, the atomic level stuff,
Right.
dictates everything, from how heavy something is, its density, to whether a huge building stays standing.
Right. And these sources, they're pretty comprehensive. Looks like solid physics instructional material. They even mention a specific physics teacher, Hakvevili Torun.
Yes, noting positive contributions to the material. It suggests a good foundation for what we're discussing. So, yeah, we're ready to unpack it.
Okay, let's dive in. So, starting really basic. You look at a solid object, seems uniform, but what's actually going on inside, atom by atom? Are they all, arranged the same way?
Oh, definitely not. That's actually the key distinction. Solids fall into two main camps based on how their atoms or molecules are organized internally. You've got order, and then you've got, well, chaos.
Okay, let's start with order. Sounds neater.
That would be your crystalline solids. These are the materials where everything's lined up perfectly. Think of table salt, NaCl, sodium and chlorine ions in this really regular repeating grid, a lattice structure.
Okay, like tiny soldiers all in formation.
Exactly. And that orderliness gives them very specific properties like a really sharp melting point. They hold their structure until they just give way at a specific temperature.
Makes sense. So what's the other side? The chaos.
That's the amorphous solids. Here, the atoms or molecules are just sort of jumbled together randomly. There's no long-range pattern.
Like what sort of materials?
The common examples are things like glass, most plastics, rubber. You interact with them all the time. And because they lack that strict internal order, they tend to soften gradually when heated, rather than melting suddenly.
Interesting. So how do we even know this if we can't, see individual atoms lining up? How did scientists figure out this crystalline structure?
Well, that's where X-rays come in. Specifically, X-ray diffraction. It's like our way of seeing the unseen.
How does that work exactly?
Well, when you shoot X-rays at a crystal, the regular arrangement of atoms acts like a tiny diffraction grating. The X-rays bounce off the atoms and spread out, but they interfere with each other in very specific, measurable patterns.
Patterns. Okay. Someone first noticed these.
Yes, von Lau first observed these diffraction patterns.
Yeah.
But just seeing them wasn't enough.
Right, you need to interpret them. The sources mention the Braggs. Father and son.
That's William Henry Bragg and William Lawrence Bragg. They provided the analytical key. They figured out the mathematics behind those patterns.
So that they could work backward.
Precisely. They developed the framework, Bragg's law, that lets you take those diffraction patterns and calculate the exact distances between the atoms in the crystal lattice. It was a huge breakthrough. Suddenly, we could measure the invisible.
Wow. And that technique, it wasn't just for rocks and salt, was it? The sources highlight its role in biology.
Oh, absolutely fundamental. The same basic physics principle used to measure atomic spacing in a crystal was used to figure out the structure of life itself.
You mean DNA?
Exactly.
Yeah.
Maurice Wilkins, Rosalind Franklin, and then Watson and Crick, they used X-ray diffraction patterns from DNA crystals. Franklin's photograph 51 was, the crucial piece of evidence that pointed towards the double helix structure.
It's amazing how a physics technique for inanimate solids unlocked the secret of life. That really shows the power of these fundamental principles.
It really does. The physics is universal.
So, okay, atoms are arranged, either orderly or messy. What's actually holding them in place? The sources list 4 types of bonds.
Right. The bonds are what give a material its inherent strength and properties. You've got the big 3, the strong ones: ionic, covalent, and metallic bonds.
Okay, examples.
Well, ionic bonds, like in salt, involve electron transfer. Covalent bonds, like in diamond, involve sharing electrons, makes diamond incredibly hard. Metallic bonds, found in metals like copper or iron, involve a sort of sea of shared electrons, which allows for conductivity and malleability.
Right. You can bend metals.
Yeah. And then there's the 4th type.
Van der Waals forces, which are weaker, it says.
Generally, yes. Van der Waals forces are weaker attractions between molecules. They're important in things like, say, dry ice, solid carbon dioxide. It's held together by these weaker forces, which is why it turns directly into gas. It sublimes so easily. The bond type really dictates how tough the material is.
Okay, so structure and bonding dictate the form and toughness. Let's talk about bulk, density. How do we measure how much stuff is packed into a space?
Density is pretty fundamental. Simply put, it's mass divided by volume. how much mass is squeezed into a certain amount of space.
We also talk about relative density.
Right, sometimes defined using weight per unit volume. But the key reference point we use is water.
Ah, yes. Water at 4 degrees Celsius, defined as exactly 1,000 kilograms per cubic meter.
Or 1 gram per cubic centimeter, yeah. Everything else is measured relative to that standard.
And the sources give some interesting numbers here. Table 12.1, we often think of gold as super heavy, but it's not even the top, is it?
No, according to this table, the densest stable solid listed is iridium. Comes in at a hefty 22,650 kilograms per cubic meter.
Wow. Gold's high, but lower.
Yeah, gold is up there at 19,300. But, what's interesting isn't just the raw number. It's why engineers might choose a dense material.
It's not just about being heavy.
Rarely just about that. Take iridium again. Yes, it's incredibly dense. But its real value in many applications comes from something else related to its strong structure, its incredible resistance to corrosion.
Ah, so it lasts.
Exactly. It's chosen because it won't degrade easily, especially in harsh chemical environments. The density is almost a side effect.
Yeah.
So density helps us classify materials, but the other properties often dictate where we actually use them.
That makes perfect sense. Understanding the basic properties helps engineers choose the right tool for the job. So, if we know the structure, the bonds, the density, the next big question is how materials respond to forces. Elasticity.
Right, elasticity. It's all about resilience. Can a material bounce back?
You mean like stretching a spring?
Exactly. Or compressing a rubber ball. Elasticity is the ability of a material to return to its original shape and size after you remove the force that was deforming it.
And this is where Robert Hooke comes in. He put a number on this.
He did. Hooke figured out the basic relationship, now known as Hooke's law. It states that the force you apply is directly proportional to how much the material stretches or compresses.
The formula is F equals K times delta X.
That's the one. F is the force, delta X is the change in length, and K is the key part, the spring constant, or stiffness. It's like the material's unique signature for how much it resists being deformed.
And that K value is crucial because there's a limit, right? You can stretch things too far.
Absolutely. Every elastic material has an elastic limit. If you apply too much force, push it beyond that limit, it won't spring back completely. It gets permanently deformed, or it might even break.
So Hooke, working alongside people like Wren and Newton back in the 17th century, basically laid down the rules for how hard you can push things before they fail.
Pretty much. It was foundational for understanding material limits, which is obviously critical for engineering.
Okay, that's the perfect transition. From the basic law to actual structures. How do engineers use these principles to make sure, bridges don't collapse and buildings stay up? Let's talk engineering strength, maybe starting with a simple beam.
Right, a simple horizontal beam holding up a weight. It seems straightforward, but there's a lot going on inside. When it bends, the top surface gets squeezed together.
That's compression.
Exactly. Maximum compression along the top. Meanwhile, the bottom surface gets stretched apart.
Maximum tension along the bottom.
Right, but think about the material right in the middle of the beam, halfway between the top and bottom.
It's not really being stretched or squeezed much.
Precisely. That's called the neutral layer, or neutral axis. It experiences very little stress. So from a strength perspective, the material in that neutral layer isn't doing much heavy lifting.
Which sounds inefficient, like wasted material.
It is, and that observation leads directly to one of the most brilliant and efficient structural shapes ever designed, the I-beam.
Oh, okay. I see them everywhere in construction.
Because they're incredibly efficient. The I-shape puts most of the material in the top and bottom flanges exactly where the compression and tension forces are strongest.
And the thin part in the middle, the web.
That just connects the top and bottom and resists some shear forces, but it uses much less material than a solid rectangular beam would. You get maximum strength for bending resistance with minimum weight and cost. It's pure structural optimization.
Smart design based on understanding stress. What about other shapes? The sources talk about arches and domes being incredibly durable, especially ancient ones made of stone.
Yes, arches and domes are masters of managing compression. And that's key because stone, brick, concrete, these materials are fantastic at resisting being squeezed. Compression.
But they're terrible under tension, right? Pull them apart and they crack easily.
Exactly. So an arch or a dome is designed to take the downward load gravity, the weight above it, and cleverly redirect it outwards and downwards through the structure itself, almost entirely as compressive forces.
So the stones are mostly just pushing against each other?
Pretty much. Think of ancient Roman aqueducts or huge domes like the U.S. Capitol or maybe the Houston Astrodome. They last for centuries because the shape ensures the material is primarily under compression, which it handles beautifully.
There's a really cool principle mentioned about finding the perfect arch shape using a chain.
Ah, the catenary curve. It's such an elegant idea. If you hang a flexible chain or rope and just let it droop under its own weight, the curve it naturally forms is called a catenary. So if you take that exact catenary curve and flip it upside down, mathematically invert it, that gives you the ideal shape for an arch that will carry its load purely through compression. No dangerous tension forces develop within the arch itself.
Wow, nature literally shows us the perfect engineering shape.
It does. The St. Louis Gateway Arch is a famous example. Its shape is a weighted catenary curve, precisely calculated for that structural perfection.
Incredible. Physics hiding in plain sight. Okay, we've talked structure, stress, shape, but there's a huge factor we haven't hit yet: size itself. Why does size matter so much for strength? The scaling problem.
This is a really fundamental concept in physics and biology. It explains so much, like why insects can be proportionally so strong and why you just can't scale up an ant to the size of the dog.
What's the core principle?
As any object gets bigger, its dimensions increase. Let's say you double its height, width, and depth. Its volume, and therefore its weight, assuming constant density, increases by the cube of that factor. So doubling the size means 2 cubed, or 8 times the weight.
8 times heavier just by doubling the size. Okay.
But the strength of many things, like a leg bone or a support column, depends on its cross-sectional area. When you double the dimensions, the area only increases by the square of the factor. So 2 squared, or only 4 times the area, 4 times the strength.
Uh-oh. Weight increases faster than strength. Much faster.
Exactly. Weight, volume, cube, outpaces strength, area, square, dramatically as things get bigger.
Yeah.
This is the scaling problem.
And that explains the insect example.
Perfectly. Small insects have a much more favorable ratio of cross-sectional area, strength, to volume weight. That's why an ant can carry things many times its own body weight. Its structure is easily strong enough for its tiny mass.
Whereas a large animal,
Yeah.
like an elephant,
An elephant is pushing the limits of biological engineering. Its bones have to be incredibly thick and sturdy just to support its enormous weight. Its whole physiology is dominated by the challenges of its sheer size, overcoming that unfavorable scaling.
like needing large ears just to get enough surface area to cool down its huge volume.
Precisely. That volume to surface area ratio is another aspect of scaling. Large things have trouble shedding heat. Small things lose it quickly. It governs everything from animal design to engine efficiency.
Which brings us to the cutting-edge nanotechnology. The sources mention working at scales of 5 nanometers or less. Why is that relevant to strength?
Because down at the nanoscale, you're playing by different rules. Or rather, the scaling laws work for you again. You can potentially engineer materials with far fewer defects and achieve theoretical strengths closer to the actual atomic bond strengths. You get incredible durability in tiny packages.
Exploiting that favorable strength-to-weight ratio at the small scale.
Exactly. And this connects to modern manufacturing too, like 3D printing.
Additive manufacturing, right. Building layer by layer.
Yes. It allows engineers to design and build complex internal structures. Think intricate lattices or honeycombs inside an object that put material only where it's needed for strength, minimizing weight and waste. It's like taking the I-beam principle down to a much finer, customized level.
That really does bring everything together. From the way atoms arrange themselves in crystals,
To the types of bonds holding them, the resulting density, how they respond elastically,
to the clever shapes like I-beams and arches that manage stress.
all the way to the fundamental limits imposed by scaling laws and how we're trying to overcome them with things like nanotech and additive manufacturing.
So the core takeaway seems to be, structure is everything.
I think that's fair to say. The efficiency, the strength, the durability of any material or structure comes down to its internal arrangement and how effectively its shape manages the forces acting on it, all governed by these fundamental physical laws we've been discussing. Understanding stress and designing to handle it preferably through compression for many materials is key.
So for everyone listening, what this means is, next time you look at a skyscraper or a bridge, or even just a plastic bottle, remember the journey. It goes from scientists figuring out atomic arrangements using X-rays,
To engineers calculating stress distributions and selecting materials.
all the way to designing shapes like that perfect inverted catenary arch, shapes dictated by physics to ensure stability and strength. It's all interconnected.
Absolutely. And maybe here's a final thought to leave you with, circling back to scaling. We saw how insects achieve incredible relative strength
Mm,
because of their small size. We touched on nanotechnology potentially doing something similar for materials.
Right.
So, thinking really big picture, if we could truly master nanoscale engineering, could we eventually build structures, entire buildings, perhaps using materials that mimic the relative strength and lightweight efficiency of, say, an insect's exoskeleton? What kinds of revolutionary architecture might that enable?
Wow. Buildings as strong as bugs, relatively speaking. That's definitely something to ponder. Thank you for joining us for this deep dive.